Bear with me, I'll make it quick. The schedule today is very exciting. 2 talks in the morning, both very machine learning focused. Long lunch like always, and then a bunch of short talks in the afternoon on a ton of different topics. So that's a nice variety that you're going to see. And our first speaker this morning is Aarti Singh from Machine Learning Department at Carnegie Mellon. And she's going to tell us about active sampling in unsupervised settings.
Great. Thanks, Luke. Well, thanks to the organizers for inviting me. It seems like it's been a great workshop so far, and I wish I could have joined earlier, but I'll be around at least for most of today. And I've been watching some of the talks, actually, just at least doing brief. So the nice thing is these are all streamed, and so we can, I guess, have access to those. So I'll talk about active sampling in the context of unsupervised learning in particular. So let me start with sort of the big level, high-level picture, which is, if this works. Yeah, OK. So everybody is talking about big data, that there's lots and lots of data out there, and we have no dearth of data, so to speak, and not so much caring about what data do we collect, right? And I guess a lot of this workshop has been focused on interactive learning. What can we learn with interactions? Why do we have to be careful? Why can't we just keep on collecting data arbitrarily? Why do we have to be judicious maybe about what data we collect, what type of interactions we do? And the motivation is clear that the systems that we are trying to understand are even bigger. No matter how much data we have, think of computer network, no matter how much we are collecting gigabytes, terabytes, petabytes of data, but it's still not enough to measure the round trip time, let's say, between any pairs of nodes in the internet, right? And we'll never have access to that type of data. Similarly, people are building fancy things like panoptic cameras, which are recording not just the intensity of value at a single pixel, but also properties of the material. They're recording spectral characteristics, they're recording the angular characteristics, like lots of different things that you basically can point the camera at something and it'll tell you what is the composition of the material there. So they're recording so many different things about it. But again, in theory, you can collect everything, but when it comes down to practice, you have to get it down to a small device, and so you can't really measure all of the interesting properties that you might be interested in. Right? Think of smart cities. We have, again, we are equipping our buildings with lots and lots of sensors, collecting lots of streaming data. But again, that data is never enough. You can't monitor things in every room or every part of a building. And it's just, we always have to make decisions about where do we put the sensors, what type of data do we collect. And again, don't have to do it for every application, but you get the idea. So when we have a limit on how much data we can collect, what can we do if we only have partially observed data? And I want to categorize into these 2, or actually I should say really 3. So I'll talk about passive sampling, which is data either drawn uniformly at random, which means you just randomly choose from the data. Here's just like a data matrix, or it could be a data tensor. But you just choose randomly the entries that you're observing in this matrix. Another thing that I categorize under passive sampling is the ability to select data, which entries you want to observe, but prior to seeing any other data. So this is what statistics literature typically refers to as experimental design. We're talking about, can I design which measurements I want to obtain, but using other information I have, but not measurements from the system. So I'll give an example of that as well. So for example, you can think of, you're given a graph, and just knowing the graph, you want to decide which location. So this could be a road network. You want to decide which locations you want to sample. You know something about that the measurements are smooth on this graph, for example, right? So you can decide the measurements. You can decide them uniformly at random, or you can decide to pick these measurements based on the structure of the graph. But it's still not active sampling, which is what I'll get to in a minute, which is really feedback driven. You observe some data, and based on that, you decide where to sample next. Okay? So both data that's drawn uniformly at random or selected prior to observing any data, I call both of these as passive sampling. And then active sampling is going to be where we selectively draw data in a feedback driven way, which could be in a streaming manner, or it could be in a batch manner where you observe some batch, and based on that, you decide where to query next. And this is relevant in many applications where we have control over what data to acquire. So we can be interactive with the measurement generation process. So in learning, say, round trip times between different computers on the internet, we are sending packets to measure these round trip times. So we can be selective about which nodes we do the pings or trace routes to. In biological context, we can be selective about which experiments we do, which drug-gene interactions do we observe. And even in a camera, right, planoptic camera, we can be particular about which properties do we want to measure and store. All right, so at a high level, we would like to understand what are the fundamental trade-offs between a lot of the resources we have access to. So I refer to these different axes as the statistical efficiency axis, where you are measuring some performance of your system in terms of some error. So it could be a risk, your noise tolerance, or error, misclustering error, misclassification error, mean square error in regression, things like this, or noise tolerance. They'll all be along the statistical efficiency axis. Measurement efficiency is how many data points do we need. Okay, so that's the measurement aspect. You can also think about communication, computation, memory, and one other one that's often not thought about as much is model assumptions. So I'll put another axis here. It's in a slightly different spirit than the rest, but this is model assumptions. What kind of model assumptions do we need to get a particular trade-off, let's say, between statistical and measurement accuracy? Which is, at least these are the two axes that people care about the most, or have cared about the most so far. Of course, now people are starting to think about some of these other axes as well, at least in statistical learning literature. And a lot of the active learning work has also focused on how can we improve this trade-off between statistical and measurement efficiency by using feedback, being clever about what measurements we are obtaining. Right? And I'll talk about how active sampling can enhance trade-off between many of these things. So in some cases, I'll only focus on statistical and measurement efficiency, sort of like the classical problems. And in other cases, I'll point out where it also leads to either computational gains, gains in terms of the model assumptions you might be making, and so on. Okay. All right, so let me start with how do we think of the power of active learning? So active learning has mostly been thought of in the supervised context, where you're deciding whether or not to obtain the label of a data point. Right? So this is I think most of the work is on classification, which basically just talks about you have discrete labels, many times just binary labels, and you're deciding, given a point or a pool of points, or you can synthesize points, do you want to collect the corresponding label or not? And can I decide which points I get a label for in a feedback-driven manner? And I want to point out that in some sense, at a higher level, we can think of the power of active sampling being whenever there is some heterogeneity in the problem, then active methods can learn about that heterogeneity using feedback, and they can focus the sampling to learn better. Okay? But sort of this heterogeneity is important, and not only does the system have to have some heterogeneity, which I'll give many examples of, but it also has to be unknown. So going back to my graph problem, if I tell you the graph, right, so I'll talk about a problem where we have to learn the graph, then I'll show active sampling helps. But if I tell you the graph and your function is smooth on it, this is actually something I didn't include in the talk, but maybe I can talk during the afternoon if there's still spots or if we have some time. But in that case, you can show that you know the graph, so you already know the heterogeneity. You can experimentally design your observations, but using feedback, you don't gain anything. So I just wanted to sort of make that point that somehow the heterogeneity has to be unknown. We have to be able to learn it from data. That's when active sampling is going to help. And in classification, what's the heterogeneity? It's the fact that points near the decision boundary are more important. Right? So if you think of what has been shown in this context, well, people have shown, including many people in this audience, Rob, Steve, Nina, lots of other people have, Shai here, right, have talked about improvements in classification settings, where in a 1D simple problem, so you have a single feature, the rates for passive learning, they depend on how quickly do the labels go from being 1 to 0, right? So this is just the probability of label being 1 given x, and of course 0 being given x is just the complement of that, right, 1 minus that. And so the more quickly this function changes near the decision boundary of half in binary classification, the rate is affected by that. And in the active context, what people have shown is if you are selective about where you are collecting the labels for what data points, you can focus collection of data points near the decision boundary, and you actually get an improvement in your rate like this. So instead of 2 kappa minus 1 here, you get a 2 kappa minus 2, which is an improved rate. Right? Similarly, for regression problems, which are slightly less studied. Now, if you think about regression in the standard context, people usually assume your regression function is smooth. If your regression function is smooth, there's not too much to be learned by feedback-driven sampling because everything is nice and well-behaved. There's no heterogeneity in the system. But as Rob and Rui and Rebecca and some other people had worked on, if you have piecewise smooth functions, so you have functions that might look like this in 2D, let's say a simple piecewise constant functions or piecewise smooth functions, then you have different smoothness in different regions, and active sampling can precisely focus on these regions and giving you an improved rate compared to passive. So going by this idea, now I wanted to talk about unsupervised problems, what kind of heterogeneities might exist, and how we can exploit those using active sampling. So I'll talk about 3 problems. The first one is learning the structure of graphical models. And in this context, the heterogeneity will come in because our graphical model, so it's going to be based on a graph. I'll define it formally. But essentially, we can say that the different nodes have different degrees. So if different nodes have different degrees, that's a heterogeneity in our problem, and active sampling can exploit that. Similarly, another problem I'll talk about is matrix or tensor completion or approximation, or a related problem is column subset selection. I'll mention some results along this direction. The heterogeneity here, again, comes from the fact that, so a lot of time people have done these problems, they assume the matrix is like low rank, you're trying to recover it from partially observed data, but they assume that all the columns are rows, have their energy well spread out amongst all the coordinates. But if you have certain spiky columns or rows, that's exactly when you again have heterogeneity in your problem, and active sampling can focus on those and yield improvements. Another is hierarchical clustering. And I think Pranjal talked about some improvements in the clustering context earlier in the week. And what I'll focus on, or I briefly mentioned results on, I don't think I'll have too much time to get into it, is hierarchical clustering, where you have multi-scale clusters. So there are some larger clusters, and within those there is further grouping that leads to smaller clusters and smaller clusters. And the heterogeneity naturally comes from that the fact that you have multi-resolution clusters. So again, active sampling can focus on that. All right, so with that sort of high-level picture, I'll start with the first application, which is of graphical model structure learning. So the problem is as following. We want to learn conditional independence relations between variables using few samples from them. Okay? So the variables of interest could be the readings at different sensors, and we are interested in learning the conditional dependency graph between all these sensors. So which sensors, measurements are dependent on which other ones, conditioned on the remaining. And we want to be able to learn this graph, so it's an unknown graph, from few observations at each node. That's one motivation. You could similarly think of trying to learn a protein interaction network, where you're interested in learning the conditional independence relations between different protein or gene expressions. And you again want to take few measurements from each protein or gene. And there are other applications as well. So formally speaking, graphical models essentially encode this notion that I and j, 2 variables, don't have an edge if xi is independent of xj given all the rest of the variables. Okay? So that's just what defines a graphical model. It's encoding all the conditional independence relations. 2 nodes are independent given everything else. And in particular, let's talk about a very simple setting of Gaussian graphical models. So we have a result for a meta-active learning algorithm for any graphical model, but at least in this case, it's computationally efficient. So let's talk about this setting where you have p variables, and they are just distributed jointly according to a big Gaussian distribution with 0 mean and some covariance matrix sigma. So in this case, it turns out that such conditional independence relations imply that if we look at sigma inverse, the inverse of the covariance matrix, then it has zeros wherever there is an absence of an edge. Meaning that if I have one entry, if I have the ij entry in sigma inverse equal to 0, then I and j are independent given everything else. All right? So here's an example of a graphical model, and you can see that, for example, x1 is only connected to x2, not to 3, 4, and 5, and so these 3 entries are 0, right? And similarly, so on. So in this case, people had recently studied how many samples do you need to be able to learn this graph. So again, the graph is between these p variables, right? So x1 through xp, these p variables, and how many samples do we need from these variables to be able to learn it well? And first, there are lower bounds which say that the number of samples, so we are collecting n samples from each of the p variables, So I'll say it's a total of np scalar samples. And that needs to scale like the maximum degree of that graph times p log p. Okay? But it can be done actually efficiently. This is just a lower bound. So it says you need at least that many examples to learn it from passive samples. Okay. And there is a corresponding matching upper bound where using a very simple algorithm, which is basically node-wise lasso, you take the measurements of every variable, you regress it onto the n samples from other variables using lasso. You put an L1 penalty, and wherever there's a 0, you don't have an edge, and you have an edge whenever the regression coefficients are non-zero. Okay? And it has been shown that in that case, that simple algorithm is able to achieve this lower bound, and the total number of scalar samples you need is the maximum degree times p log p for this algorithm under the Gaussian graphical model setting. Right? So if you think a little bit more about passive sampling and what it requires that you have n samples from all of the variables from this big joint distribution, and we are talking large scale, right? So p is large, that come from this joint distribution, right? Now, in any application, if you think about, for example, the sensor application or this gene-gene or protein-protein interaction network, collecting such measurements is very expensive, right? Because you are talking about, well, one, being able to synchronize all the sensors. So to obtain one sample from every node, we are saying we are sampling from this big joint distribution. You need n samples from all of them, sort of one sample has to be sampled from the joint distribution. So there is a cost of synchronization and of course also cost of measurement. You're requiring that you get expression levels of all genes or all proteins under a particular, let's say, drug, right? Which might also be expensive. So in practice, you have limitations that may not allow you to do the synchronization or do the measurements of all the variables together. So in that context, we can talk about active sampling. And here's a meta framework that we can use. So we can say that we are going to select a subset of these p variables at every round. And we are going to obtain some NL samples from each one of those variables. All right? And we just keep doing this round. Every round, so we start with some subset, and we collect some number of measurements from them, and then we discard some of them, which we think we have learned their neighborhoods, and then we keep focusing our samples on the harder and harder variables that have more complex dependency structures, and we collect more samples from them. And we keep on repeating this process, honing in on the more complex one. And how many total samples we need? So again, comparing to the n times p for passive sampling. Now, if in every round we are using NL samples from SL, which is our subset of variables we are sampling from, we need sum of NL SL number of samples, right? Yeah.
The SLs, you pick them or randomly?
Yes. No, we'll pick them. Yeah, I'll tell how we pick them. Yeah.
So does the lower bound for the passive case imply that, you know, if you were to somehow passively sample subsets of this kind, you need p times the number you showed us? P times d times?
If you randomly sample, yeah, it applies to, so they construct a hard enough class for which you can't, that random subsampling wouldn't give you anything. It still requires, yes, on the graph would still require, yeah, degree max number of samples. So yeah, you can't do this with random sampling. That it's a lower bound for all passive sampling methods. So how do we do this? So it's a very simple procedure. We start by exactly as I said. We are going to take some samples. So we are going to take some samples from all the nodes, but very few samples. So we might, it's not perfect in the sense, if you're practitioners, you will say, I don't even want to have any number of samples from all the variables, okay? So we haven't solved that problem. I'm very interested in how we can solve that. But what you can do is you can take a small number of samples from all the variables, and then you can try to get an estimate of their neighborhoods. Now, some neighborhoods will be correct and some will be wrong, because for some you won't have enough samples to learn all the dependencies. But for the ones that are correct, you can use half your budget to do the learning of the neighborhoods and half the budget to verify that you have found the right neighborhood. And then you can stop sampling from them. That's the basic idea. Okay? So it's a very simple idea. So the algorithm proceeds as follows. We take, so initialize L is just a counter. We'll initialize it to 1, and we'll collect some constant times L log P samples. P is the number of variables in this. From everything that initially the xp/settled set is everything we haven't settled or stopped sampling from. So initially it's everything. And we take that many samples, we are going to use D1 for learning and same number of samples for verifying the neighborhoods. And then sequentially for every node for whose neighborhood we haven't found, we are going to learn their neighborhood and verify their neighborhood. Right? So we'll just learn the neighborhood using lasso. The only thing we need to be careful about is that we enforce that lasso does not return, or it can return a larger neighborhood, but we restrict it to L1, or L. Whatever is our current iteration size, we restrict the neighborhood to be of that size. It cannot return more than that many non-zeros. We just take the top L. Okay? And that's important to make sure that the number of samples you have is enough to do the testing, the verification of the neighborhood. All right? And then you verify the neighborhood by basically saying, now I have learned some neighborhoods. I'm going to condition on these variables that are in my neighborhood, and I'll check whether this variable is now independent of all the other variables once I condition on this learned neighborhood. And we do that test using the second half of the samples. And if the partial correlation with all other neighborhoods is small, then you believe that you have found the neighborhood of this node, otherwise you have not. Right? So there's one more refinement to what the meta procedure that I had explained, which is if we find the neighborhood of a node, we don't stop sampling it immediately. We actually have to make sure we also have found its neighbors' neighborhoods. Because we need its neighbors' neighborhoods, we need it to find its neighbor's neighborhood. Okay? So we have to keep sampling until you get the neighborhood of that node and of its neighbors, essentially. Okay, but once that's done, you add it to you stop sampling from that node. And now you just double your budget, so L is affecting your sampling budget, you double that, and you start again with the remaining nodes and keep on doing this. Right? And you stop when you have exhausted your budget or you have found the neighborhood of everything.
So now, once you've found, or you've settled or whatever, a node in this graph,
You stop settled means you stop sampling.
look at the marginal distribution.
Exactly.
That remains, but you kind of know how to marginalize as you know the neighborhood, or you just
Marginalization just means I'm stop sampling from these, I'll measure from the remaining, right? I just take a measurement from the remaining.
Would there be some possibility of, say, a hierarchical Bayesian approach to not have to sample from all of the variables at the beginning? If you sample from some subset, then you'd learn something about some of the others from the other variables. If there was some underlying Bayesian assumption associated with the Gaussian parameters.
Some kind of a Bayesian assumption, but this is all, as I was saying, like the heterogeneity here, which is the neighborhoods we are trying to discover, are unknown. So how would you impose such a prior? Somehow, to come up with such a prior, you would need information about the varying degrees, right?
Well, the degrees, wouldn't there be then some sort of correlation between the degrees of one node? I mean, so like, for example, there's presumably some underlying true Gaussian that you're trying to learn.
Mm-hmm.
And so here, in the current case, there's no assumption behind the degree of one node and another node, but there could be some shared assumption, like the parameters. I mean, it's standard hierarchical Bayesian assumptions where you don't need to know everything to know everything. You know, some such
Okay, maybe we could talk offline about what exactly you have in mind. But if you have such other prior information, which is like the two nodes are related in more than just what is given by the graphical model, the conditional independence relations, sure, you can bring that to bear. But I'm happy to talk more offline.
So if you have some sort of hub nodes present in the graph, then that last bit about neighbors being included seems pretty bad, because you need more samples for the high degree node to get learned, but till it gets learned, all of its neighbors also have to stay around.
So actually, yeah, this can, so first of all, I mean, that's an important point. The whole thing here is that yes, you will collect more samples from the hub nodes, less samples from other nodes. But you're pointing to that now all the neighbors of the hub node will also, you can't stop sampling them. It turns out you can. I think we can tighten the algorithm to do that. So yeah, if you're thinking of a star graph, once you have learned, you can basically learn the neighborhoods of all the remaining spokes, and you can guarantee that the algorithm will then, you would have already learned the neighbors of the hub guy, and you can stop sampling. So it's just not coming out in this, but yeah, the algorithm will naturally do that.
So the only mystery parameter in here seems to be that the chi.
Right.
So is that just controls sort of the accuracy? I mean, something having to do with the...
So this basically depends on what is the smallest entry in your inverse covariance matrix. And even like passive algorithms assume that that's lower bounded from below. If it can be arbitrarily small, then of course, yeah, you're in trouble with both passive and active.
You could just do an outer wrapper where you start with a half and then a quarter.
You could, though I don't think I've seen that even for the passive case algorithms like that. They just, but you're right. I mean, if that quantity itself could be arbitrarily small, right, the smallest entry, that's also a heterogeneity in your system. You can adapt to it, right? You're absolutely right. That's the way at least I think of it, that yeah, that your conditioning could be bad. Like there are so many things we are holding constant here, which could be bad. But once you say that they are bad, means that now you can adapt to it, right? Yeah, but that's a good point. Akshay, do you have a question? Oh, okay. All right, so what do we gain by doing this procedure? Now we can show that the number of active samples that that are sufficient to recover such a faithful Gaussian graphical. So all the assumptions are the same here. Dmax j, I'm going to indicate as it's not the maximum. So earlier we had the maximum degree of the graph. Now I have the maximum degree of any neighbor of jth node. So this is a very local quantity. It could almost be the degree of that node, except we also have to sample it for its neighbor. So I think you might actually be able to improve this to just the degree of the node. But right now it's the maximum degree for every node. It's the maximum degree of its neighbors. And so basically you can show that the total number of scalar samples you need now scales like the sum of all these local degrees times log p, versus being the maximum degree times p log p. Or another way to think of this is how many samples am I collecting per node on average? Instead of d max log p, now I'm collecting d average log p, roughly speaking. Right? So it's like it scales like the average degree. Or you have made the number of samples needed per node adaptive to its local degree. If it's easy, if it's an independent node, you collect very few samples. If it's connected to only one other node, again you're collecting few samples. But if it's connected to a lot of nodes, then you are paying a price for that correspondingly. All right. So yeah, one is that you get sort of this average of the local max degrees instead of the global max degree. So it's better for skewed degree distributions, which is almost always the case. You never have uniform graphs in practice. And it also minimizes the need for synchronization, at least to some extent, that you only need synchronization in the very initial stage for few samples. Of course, the question of can we do this without requiring synchronization of all the nodes even once is open. I don't know how to solve that.
Do you know how this quantity scales for like preferential attachment model or something like this?
So we've done simulations, and those are exactly the cases you see improvement for power law graphs and so on. But I don't have a quantification of it. Yeah, so that's a good question. You could try to quantify it in that context.
Is this local Dmax? Is this necessary? Are there lower bounds?
So there is. Okay, I almost shouldn't say it. There is a paper on arXiv, let me say it this way, which does show a lower bound. It just came out recently. It has, I think what it shows is that you get dj, not dmax j, which we don't know. On one hand, it seems like, yes, you probably can adapt to the local degree, but because, I mean, in a hub-like context, you can sort of do, it seems natural to do that, but I don't know if you can completely close the gap between these two in general. Yeah, we thought about this for a while, haven't been able to close that gap yet.
So just for the lower bound instance that's used in passive, so is the lower bound such that I can give it sort of an arbitrary degree distribution and still it will force a dependence on Dmax, or is it using a very specific type of degree distribution to construct a lower bound instance where Dmax?
For the passive case.
Yeah, for passive. Like I'm just wondering, does the lower bound instance actually have a lot of heterogeneity in the degrees, and is that?
It has heterogeneity. But it's heterogeneity in the sense of, I think they consider like a clique versus nodes that are independent kind of thing. So there is heterogeneity, yes. Yeah.
So I'm just a little bit confused about the bound, because for the star graph.
That's what Alec had asked about.
Oh.
So yes, if it's a star graph, right now it says that, yeah, it's no better than random or passive sampling. But the algorithm will actually, like in that case, once you discover the neighborhoods of all the spokes, right, you can settle the hub also because you have discovered its neighborhood, right? But in general, so I think of this as on a larger scale where you might have multiple hubs and there are lots of graphs that have, yes, the hubs are connected to a lot of things, but then there are a lot of other nodes as well.
I think there are some recent results about even passive graphical model learning that they related not to the Dmax. It can be Dmax,
Right.
but they relate it to the sum of the degrees. Or, I mean, for the star graph, for instance, it can be better.
Okay, but I'm saying that I think this can also be improved for the star graph. For star graph, in fact, this would just be the degree of the, I mean, it will just be the degree of that. Actually, it won't be the degree, it will be just one. I mean, the degree will correspond to just the spokes. It won't correspond to the hub in general. So in terms, like the algorithm will do that, but the bounds right now sort of, because you were saying you don't know when that happens, you don't know when to stop, right, has this behavior. But for a given budget, if you compare passive and active, you will see that the improvement there. All right. So yeah, actually, if there are more questions, we can talk about those, because otherwise I was going to move on to another problem. And also, could somebody keep track of time? If yeah, I can stop whenever needed.
So the various incoherence and eigenvalue conditions, is that also, I mean, are those also just things you could potentially have?
Yes, absolutely. Yeah. So right now we have, as I mentioned that, plus incoherence and restricted eigenvalue conditions, they are exactly the same as for the passive case. Both of them are holding these as constants. If these can be, yeah, you can allow heterogeneity in it, that they could be different for different nodes, right, or different, yeah, subsets of nodes could be different in terms of restricted eigenvalue. You can adapt to that also potentially. Yeah, I can say more offline maybe, but yeah, for now. Okay, so now I wanted to move to this problem of matrix, or like I guess I'll mostly talk about matrix completion. The same results can be extended to tensor completion as well, and what we can do with active sampling. So here the goal is we have a matrix that we want are only given some entries, right? And we want to be able to complete this matrix. And the active question will be that those entries are not uniformly sampled at random, but we have control over which entries to observe. And again, this can happen if you're interested in learning, say, round-trip times between some hosts and clients, right? We have control over which ones we measure in a computer network. We have control over which drug-gene interactions we measure. Even in recommendation systems to some extent, not completely, but like you can choose how to design your survey, basically, or commodities to ask a user to rate. Again, not completely, but in some applications you can do that. Right? So if you look at all the work on trying to do this completion of this matrix, they assume that the matrix is low rank or near low rank, and talk about when you can do the reconstruction. And one thing that comes up is this incoherence or Leverett score notion. So basically the idea is, if I have a matrix like this, all 0, so green is all 0, one non-zero entry, there's no hope. You can't recover it from partial data at all, right? Partially observed data. Very few entries in the matrix. You need to observe all the entries to be able to find it. And so what most of the papers, or all the papers on passive matrix completion assume, is that your matrix is both row and column incoherent, which means that sort of, if I look at, well, I'll give a precise definition, but essentially the energy in your rows or columns are uniformly kind of spread out amongst all the entries. Okay? And what I'll talk about is when active learning buys an improvement is when you can have this kind of a situation where it's spread out, but it only needs to be spread out in one direction, only the rows or the columns. So they can be spiky columns, if you will. I think I mostly focus on, yeah, allowing the columns to be spiky. Okay, so formally, this definition of coherence is you are looking at, so U is going to be a subspace. In this case, it's, let's say, the column subspace or the row subspace. And we look at how aligned it is with any of the canonical basis vectors. So if I take any single entry, how much does the projection onto this column space look like? How spiky is it, essentially?
Is this spiky column or whatever model motivated at all by these applications? Like, is that...
So you can have like anomalous genes and anomalous, right, that you might want to spend more sampling to learn more about them, whereas other genes who are predictive of other genes, you can, sample less from them. That's the idea. Right? Similarly, in computer networks, if it's, these are nodes within a subnet, I think you did some work, you can sort of predict them from each other. But if they are in, you at least want to get sort of representative samples from different. Yes, in some applications it can come up. Again, we haven't like worked on one specific application to show that, but it's motivated by that idea. So, I just wanted to mention the connection to Leverett score. So basically, this quantity is precisely the unnormalized Leverett score of the ith coordinate if the U subspace is the subspace spanned by the top k principal components, right? So that's why these notions are very related. Except the coherence, you do the n by k up front, where n is the dimension of the matrix and k is the rank of the matrix, or at least the rank that you care about approximating. So in this case, there are lower bounds which show that the number of random entries necessary to recover an n by n matrix of rank R with row and column space coherence bounded by mu. So both of them have to be bounded. Energy has to be well spread out. They look like mu R log n per column. Okay. So I'm again going to state it per column. If you care about the total complexity, you can just multiply it with, it's an n by n matrix, it's n mu R log n, which is pretty close to, in some sense, what you can expect, because there are nr degrees of freedom if it's a rank R matrix of size n by n. There are nr degrees of freedom. This is sort of the best you can hope to do, right? So this only, the mu comes in. It's the natural notion, as I said. Mu is the incoherence, right? That comes in, and log n is just a small extra price. You can potentially hope to improve that. That's all there is. And there is a matching upper. Actually, there are many matching upper bounds, but here is one of them. They're optimal in different contexts, but this says that the number of random entries sufficient to recover such a matrix, which is precisely rank R n by n, with row and column space coherence bounded by mu, scale like mu R log square n per column. And you can achieve it using, let's say, nuclear norm minimization, right, which is a convex formulation. You're saying, find me the matrix that matches my observed entries while having the smallest rank. Here, the nuclear norm is a surrogate for, convex surrogate for the rank. Okay, so what can active sampling do in this case? And first, what does an active sampling algorithm look like? Well, we can say that we start in a purely sequential manner, and we draw some number of entries from a column, and we check if it lies in the space spanned by the previous columns we have observed. If it does, we don't need to collect any more entries. We can just complete it using the existing number of columns. But if it does not lie in the space, then we observe all its entries, and we add it to this subspace, candidate subspace we are maintaining. Okay? So that's the simple algorithm. You start with the first one. You don't have anything to project onto, so you observe everything, right? It doesn't lie in the space spanned by whatever you have. You observe everything. For the next one, you check whether it lies in the space spanned by the first one using, again, this step requires a test where you're testing a partially observed vector using a fully observed subspace, right? And Laura and Rob did some work on saying when this test succeeds, you can show it succeeds with what probability, and those are exactly the results we'll port to this setting to talk about what is the improvement you get in terms of actively sampling this matrix. So what is the improvement? Well, essentially what happens is that R of the columns, because the matrix has rank R, get fully observed, and all the remaining you just observe some M entries, which is your initial budget that you have for every column. And as long as that initial budget scales like mu R log square R, where the column space incoherence is bounded by mu, we only need now the column space incoherence to be bounded. Row space does not have to be, incoherence does not have to be bounded, and so your columns can be spiky. Okay? So row space coherence implies columns can be spiky. And then the algorithm recovers this matrix with high probability using only essentially, that R of the columns are fully observed, so NR comes from that, and N2 columns have N entries observed. That's where you get the N2M, right? And plugging the requirement on M, we get you need to sample N mu R log square R number of entries. Okay. And we can also talk about the runtime. So it runs in time, which is essentially, if you think of it as an n by n matrix, it's linear in n, or sublinear in the matrix size n squared. So in this case, actually, I just chose a very simple example of exact low rank matrix just to show that you get a bunch of different benefits by using this active sampling algorithm. One is that in terms of measurement complexity, I mean, again, there wasn't too much to squeeze out anyways, because I told you a low rank matrix of rank R, which is n by n, has only nr degrees of freedom. So you see that all we do is get from mu R log square n to mu R log square R, right? So some people call it an exponential improvement, right? Because you're getting from a constant to log n, but it may or may not. But I think the interesting thing is that it's independent of the matrix size, so that's maybe one way to think about it. How many entries you need per column does not scale as I add more movies into your matrix or more drugs into your design, sort of, right? That's one way to think of it. In terms of computational complexity, anything to do with nuclear norm minimization, most of the algorithms are about like you do some singular value thresholding, and doing that requires n square r times however many times you are doing that, some kind of repetitive SVDs. So the complexity scales n squared, and this algorithm, because it's like doing it just in a very purely sequential manner, its complexity is linear in n. I think that's the point to observe, linear in n or sublinear in the matrix size n squared. And it actually runs very fast. So if you compare it to the singular value thresholding algorithm on some large matrices with rank, let's say 100, here instead of it can do it in 5 minutes instead of 2 hours compared to the passive. It also, another thing is it's completely sequentially processing the columns instead of being non-sequential, right? Which most other algorithms are. You require the entire partially observed matrix up front. Even in terms of memory complexity, again, I mean, this can be improved for passive. I'm not saying that you can't improve it for passive. In fact, I think existing recent algorithms are able to improve it. But this algorithm only requires NR, because you're only storing that subspace that you're maintaining, and that requires n times r entries. But I think the most important part, actually, according to me, is none of these. It's really the fact that you have increased the class of matrices you can handle. And this goes back to the model assumption thing I was talking about, right? That your sample complexity is sure a little bit improved, but you have improved the sample complexity for a much larger class. You're allowing matrices that can have spikes. That's exactly what active learning is buying you, right? In fact, if you, and I've had the example here. So if you look at, here's an example of a matrix with coherent rows, which means spiky columns, then you see that this is the pattern that the active algorithm has. It's taking some random samples. From most of the columns, it's only taking few samples, and then there are some columns from which it observes them almost in full. So it's focusing on these harder examples.
If, as a practitioner, I do not know if my matrix is row or column incoherent, is there a way to adapt to that?
Is there a way to adapt to it?
It's one of them,
yes.
but I don't know which one.
You don't know which one it is. You can adapt to it. Let's see. Well, one simple thing you can do is do it both ways. But can you do it? In terms of theory, it'll work out, but there can probably be a better practical algorithm that does it. The good question. In practice, you would care about that. So here are some just showing the gap between, if you actually design matrices that have incoherent rows, in addition to columns, then you don't see any improvement, but you see an improvement when there are coherent rows. All right, and in fact, so this was work done with Akshay, who's also here, and he also showed this lower bound, which says that the number of passive entries necessary to recover an n by n matrix of rank r with only column space coherence bounded by mu, where we don't make any assumption on the row space incoherence, is actually n per column. So you basically need to observe all the entries in a column to be able to do this using passive entries, any kind of passive entries, again, whether these are somehow experimentally designed or random, any distribution. So active sampling is necessary to handle coherent rows. And again, going back to I want to emphasize this idea again, that if we look at the comparison I mentioned earlier was actually in some sense unfair to active sampling, because for incoherent matrices, you get a slight improvement. But really, this is the way to look at it, that for row coherent matrices, random sampling would require n per column, but we require only mu r log square r per column. So you're getting a big gain over a larger class. How much time do I have, or none?
You've got about 45 minutes so far, so
okay.
you go a little bit longer.
So I guess what I can do is quickly summarize the results. I won't go into detail, but you can talk about what happens if the matrix is not exactly low rank. You can show similar results. So in fact, what I thought about doing was showing those results for matrix approximation, not completion, because our matrix is not exactly low rank. You care about, can I approximate the best rank K approximation of the matrix using only partially observed data. And I'll show the results in the context of a different problem, which is column subset selection. So column subset selection is a very related problem. The goal is again to be able to, usually it's done in the fully observed setting. I'll ask the question in the partially observed setting and say, if I only observe some entries of a matrix, can I find columns that give the best rank K approximation to the matrix. So usually you don't necessarily have to return, like if you only care about approximation, you may not care about am I finding columns in the matrix, but here that's the question I'll ask. We also have results for the noisy, just low rank approximation problem, but I think this is slightly different and gives results for both. So why would this be interesting? Well, in many of these applications, you might care about, can I find the features in these unsupervised problems that are most representative, like most representative genes or drugs, which users are reflecting the behavior of most other users, or which routers or nodes, again, they sort of handle most of the traffic. Right? So in the sense that specifically which columns are the most relevant ones, can I find some that are give me the best rank K approximation of the matrix? Okay. So I'll skip over this. I'll skip over the algorithm. Essentially, we took all the or at least 2 or 3 algorithms that exist for column subset selection, and we asked the question, what happens if we do it using partially observed data? And you can talk about what happens with partially observed data, and you can talk about what happens if I actively choose those. And basically, the same kind of idea goes through, that if you have coherent rows or columns, then active sampling can focus on those. So I'll just show this. So this is just one algorithm that adapts the iterative norm sampling algorithm, where you estimate the norm of a column, and you sample proportional to that, and then you subtract off that column from the space of this matrix, and then you you basically project all the columns onto the orthogonal space, and then you repeat this procedure. Now you can do this with partially observed data, and now you can adapt how many entries. So you initially only observe some random entries, estimate the column norm, sample according to that, and then you can observe it in full, right? So same kind of idea. I'll just show that in this case, and one reason I chose to show this result for matrix approximation is you actually get a relative error bound. So if your matrix is low rank plus noise, you can actually show you get 1 plus epsilon approximation in terms of the best, so R is the best residual norm you can have, right? So a lot of the noisy matrix completion results give an additive error here, which means that the error does not go to 0 if your matrix is actually low rank, whereas here it would. And the complexity, sample complexity, again, there's no gain, in fact. In fact, we have slightly worse K square instead of K. So K here is acting as a rank because you want a rank K approximation. It's slightly worse, but actually in simulations, we see it could be tightened to NK. So it's really in theory that we still have K square here. And still the main idea is that you can get this while only needing column space in coherence. Okay. So again, these were the simulations. I'll go over that. And we did this for, as I said, many algorithms, norm sampling, leverage score sampling. And basically, the main things are that you can get almost the same results as the fully observed settings. The only things that are different are slightly worse factors, which are constants, at least for this case, right, mostly. And you require some assumptions, the incoherence assumptions, but one-sided incoherence, not both sides. And what the sample complexity is, now you're able to do this with much fewer samples than in the fully observed setting. So the only thing I'll say about this, I'll just use this as my last slide, which is, I think, since Pranjal talked about active sampling for clustering, I just want to say that, again, you can see similar benefits. So if you have the problem of I have n objects, and here's an n by n pairwise similarity matrix between them, how many entries do I need to see to be able to recover this clustering? And you have heterogeneity either in the form of different size of clusters or the fact that you have multi-resolution clusters. Both cases, you can show that instead of all n square entries in this matrix, you need only n log n here and only nk square here if k is the number of clusters you have, but they are of different sizes. This was done by Niralon, Yudongshen, and Huan, where they show that you can break the root n barrier for stochastic block models, if anybody's familiar with that, because you can essentially focus sampling. You find the largest cluster, remove it, and then you keep focusing your sampling on the smaller ones. Okay. All right, so with that, I'll and not talk about some other things. A lot of people have contributed to this that I'd like to acknowledge, including Akshay, who's here, and Nina, who's one of the organizers, and a list of relevant papers.
So one question is, you were talking about all sorts of sort of compelling applications, and so presumably for some of those, people have come up with plausible generative models for graphs, right? And is it sort of known what kind of incoherence one would expect? Would it vary with n?
Would the incoherence condition you're saying, for example, if I think of it as a Gaussian graphical model, would that vary with n? I'm not familiar with that literature, but I would say, I mean, in practice, yes, it would vary. So ideally, you would want to adapt to all of those conditions, right? That's right, because it's about, well, what is this, how weak can the partial correlations be? They can be very weak, right? Some nodes will have very strong partial correlations with their neighbors, whereas other nodes will have very weak, and you could potentially try to adapt to that. And yeah, I can imagine in the applications that would happen.
Is it possible to mix active and passive sampling?
It is, but most often then you are back to the, at least in theory, you're back to the passive sampling rate, that the improvement you get is not like a polynomial improvement or exponential improvement. But in practice, people do that all the time, actually, to safeguard against things. Yeah.
Just a technical question. So for column subset selection stuff that you're talking about, so if one were in the fully observed setting, you wouldn't need the
incoherence conditions, yes.
So is there sort of
but that's necessary. Like you can show a lower bound. I think we have it in our paper that, yeah, if you don't, I mean, it's just, yeah, it's a very simple idea, right? You need incoherence, otherwise you can't do anything with partially observed data. So remember, all the existing results are for fully observed, right? You are given the whole matrix, you just want to approximate it.
And even if you want just some relative error, still you need
yeah. From partially observed data. Yeah. Okay. Thank you.